this computer, and I want to just initially share with you my PowerPoint. And if you got any questions while I'm talking, this is the time, obviously. All right, share PowerPoint. And what we're talking about was black body radiation. And the guy that comes up with the final answer is a guy named Max Planck. And he develops this Planck radiation law, which of course solves something that, if you saw the video, resolves a classical problem called the ultraviolet catastrophe. If you go to just classical E&M and statistical mechanics, which many of you will take from probably Dr. Tech, when did he teach it last? I think he'll teach it again next year, so you'll take it as juniors. You'll see that you can develop that Rayleigh-Jeans formula, and it's just wrong from classical mechanics. And so Planck comes up with this expression that I realize I didn't talk about one of the terms, assuming you knew what the Boltzmann constant was. So I'm going to refresh that. You just got a bunch of constants out front. This black body radiation law goes as 1 over lambda to the 5th. Who knew? But more important is this term right here, okay? Because that gives you the shape of the wavelength versus, so wavelength versus what we're calling script I here. I sometimes call it the power spectral density. I've heard it referred to as the spectral density. It has all kinds of different names, but it is the shape of this curve. And more importantly, I guess the units are watts per meter squared, or maybe kilowatts per meter squared. And then you look at that for every either micron or nanometer of wavelength. Okay, so if you pick the 1 nanometer or 1 micron, depending on what you have in the denominator there, band right there, it would tell you what the intensity is in that band. And that's why people determine a spectral density, because it's only telling you what it is in that particular spectral band, or that particular spectral band, or that particular spectral band, okay? In any event, what's in this shape of this curve is a factor nobody thought would be there. Now, I didn't talk much about it, and I don't know that everybody realizes energy, thermal energy, is given by this KT right here. K is called the Boltzmann's constant. And when I made the video, it didn't dawn on me that perhaps you'd never seen that before. And that's, by the way, different from the Stefan-Boltzmann constant that we're going to talk about here in just a second. Okay, so there's Boltzmann, Boltz, B-O-L-T-Z. It's funny. My advisor in graduate school, the guy who was my principal dissertation thesis supervisor, he had a dog he named Boltzmann. Okay, so that's Boltzmann's constant. It's just when you look up, obviously it's energy per temperature, right? Because you multiply by temperature and you get an energy out. And it's just the constant that relates temperature to thermal energy. Boltzmann gets credit for that. I think it's 2 N's actually.
Should we be seeing your screen right now?
Yeah, you're not. I always hate that. I sure, man, because I didn't hit the second button. There you go. See it now?
Yes.
Okay, sorry about that. I apparently didn't hit the button correctly because it didn't register, and now I see the green border. Anyway, so this is Planck's radiation law, and there's constants out front. It goes as lambda to the 5th. Who knew? But this thing that I put in parentheses gives you the shape of the curve that we're going to look at here in a second. And we're looking at the denominator piece right there, energy being equal to Boltzmann's constant times temperature. And when I made the video last night, it didn't dawn on me that people might not have known that. I don't know if Dr. Tech covered it in first semester. If I certainly didn't in second semester. Maybe you saw it in the chemistry classes where you often see this. So Planck is looking at the total energy in a black body radiator, one of those cavity deals that's heated to a particular temperature. And that's the total energy of the cavity. And the shape of this curve was related to this other term, okay, HC over lambda, which you could just as easily have called H times F, where H is a really small number and the constant gets named after Planck himself. And so up in that exponent, you've got the ratio of the energy in a particular oscillator in this black body radiation, because that's what he's assuming that is happening. At the cavity walls, he's assuming that there's simple harmonic oscillation. And then the amount of energy in that in a single oscillator is H times F. And he's ratioing it to the total energy of the black body, which is related to its temperature. And that little fraction in the exponent of a 1 over e to that fraction minus 1 gives you the shape of this curve here. Amazing curve fitting. But what comes out of it is the notion that these oscillators have discrete energies equal to this constant times the frequency, or the constant times the speed of light over the wavelength, because you should recognize that's also the frequency. So some kind of fancy curve fitting by a brilliant German mathematician comes up with this equation that is not uh, not based on classical electricity and magnetism or statistical thermodynamics, which was also classical and known at the time. It's some completely different thing that's going on that requires a quantized energy, is what we say, a discrete amount of energy, HF. And then all other energies of these oscillators, all other energy you can have must be multiples of this H times F. And the reason given for why nobody ever noticed it before is if you look at the magnitude, 10 to the minus 34, it's just so small that nobody recognized there is a granularity to energy. But the granules are just so small that we always thought it was continuous before Max Planck comes with this equation. And so that's the significance of it. Okay. Again, you might not have been viewing my screen when I said this. This I here has units of watts per meter squared, which is intensity. The optics people invented that, but acousticians do too. Anytime you take power over an area, you're talking about how much energy per time is hitting a surface area. And it's called a spectral density because we're dividing through by a wavelength, either in microns or nanometers. And that's what I'm talking about right here. What's the intensity in that band? Or what's the intensity in that band? Or what's the intensity in that band? And so that's the quick and dirty explanation behind Planck's radiation law. Okay, and so what does that do for us for problem solving that we're going to work with? And this is today's work. There's the shape of the curve at various temperatures. Somebody drew these out. And a guy named Wien comes along and he goes, all right, and he does this actually before Planck comes up with his equation. He said, is there an empirical relationship between that wavelength right there at the peak, that wavelength right there, that wavelength right there, that wavelength right there, and the temperature? And sure enough, he finds there is. That if you take the temperature and you multiply by that peak wavelength right there, you get a constant. Again, who knew? And so there's the Wien's displacement law constant. You can see in this form, I've solved for the wavelength as a function of temperature with this constant. You could do just the opposite. If you knew what the wavelength was, you can get the temperature. And if you think about it, that's how those non-contact thermometers everybody is using right now to make sure you don't have COVID-19. They point the gun at your forehead. What that gun is doing is it's doing a quick sample of what your curve looks like based on what your temperature is. Okay. It picks off what the peak wavelength is in that it very quickly gathers this spectrum. It sweeps through a bunch of wavelengths. It doesn't need them all. It just needs the ones near where it expects your body temperature to be. It takes that peak wavelength then, and using this relationship, calculates your body temperature. And so that's how one of those guys work. And if you don't know what I'm referring to, because nobody's ever done it to you, it's one of those guys. Okay. And of course, we usually think of all of this happening on the astronomical scale. We're using this for the sun's temperature, certain stars' temperature. It works for a human being's temperature too. The law is universal and works at any temperature. Okay, so in any event, there's Wien's law. That's the first thing we're going to do some calculations on today. And then the second thing is these guys Stefan and Boltzmann, the same guy that the Boltzmann constant is named after. He's working now with a guy named Stefan. He goes, well, what if you find at say 1800 Kelvin, you integrate, you find the total energy under that curve right there. And it's actually intensity, because remember we said the Planck equation gets you watts per meter squared per whatever you got as the units on your wavelength, whether it's nanometers or micrometers right there. We'll go with micrometers. Okay, so that's the intensity uh, per wavelength band. And so if you integrate over all wavelengths, you get just intensity, watts per meter squared out, joule per second per area, how much energy per time is hitting a surface area. And so that's what Stefan Boltzmann do. And they figured out before Planck came up with his distribution. Both Wien and Stefan Boltzmann do this work before Planck. They figure out that the total area under the curve is proportional to temperature to the fourth power. And of course, they introduce a constant of proportionality. In fact, they need two. They need one that gets named after them. This sigma right here is known as the Stefan Boltzmann constant, 5.67 times 10 to the minus eighth watts per meter squared per Kelvin to the fourth. And then for a perfect black body, this other constant is called emissivity. For a perfect black body, it's one. As a person, you might not have be a perfect black body. If you saw what we mean by a black body from the video, you're really not. You got hair, you might have clothing on. A black body is a cavity carved out of the middle of a piece of metal with a hole in it. And that's all we were talking about. How well can you be modeled by that? Well, maybe 70%, 0.7 or 0.6 or something like that might be your emissivity because of things like hair and clothing and all that. But we still use the model anyway, and we often assume emissivity is one for most problems unless we're told otherwise. There are people who've tried to tabulate what emissivity is for various objects. Truthfully, above and beyond this course right now, we're going to pretty much assume everything's a black body when we do our calculations. In any event, that's what we're going to be working with today. You can see the units have to be Kelvin to the fourth because temperature is to the fourth, and also the units in the Wien's law is Kelvin. So that means if you're looking at your body temperature, like in Celsius, 37 degrees Celsius, well, obviously you got to add 273 in order to convert it to Kelvin. Right? Typically, astronomical temperatures were already in Kelvin. Pretty remarkable stuff. I should tell you that on Wednesday, we're going to come back and we're going to verify theoretically from Planck's work, from Planck's equation, from that thing right there, that script I, we're going to verify that Wien's right and that Stefan and Boltzmann are right, because everyone here is capable of taking a function, mathematical function like this script I right here, and taking the derivative with respect to wavelength and setting the wavelength equal to 0. And so for any curve then, that should allow you to calculate those peak points right there, right? And similarly, what Stefan Boltzmann do, they find the area under the curve. And so what the other half of you are going to do, well, you'll take Planck's law right here and you'll integrate it over all wavelengths and see if you can recover the Stefan Boltzmann equation from that. We'll give you most of the period to work on that because the integrals and the derivatives are not trivial to work. But that's for Wednesday. For today, we're just going to work with Stefan Boltzmann's law and Wien's law and do a couple problems, and I've got those set up. I do want to show you one animation before we go, because I think it's pretty good at demonstrating what a static graph doesn't do. So I'm going to stop sharing this with you, and I'm going to go over and hopefully hit the buttons correctly. There it is. This is one of those FETs done by, I guess, who is it? Michigan State does these. And hopefully you're seeing a Planck distribution, the curve in red, right? And you see it's called a spectral power density. In this case, they're going megawatts, capital M, per meter squared. And then per frequency or per wavelength, they're going with micrometers, microns. And in optical frequencies, most people talk about nanometers, hundreds of nanometers. So you can see right here with Planck's distribution, for the sun's temperature is what I've got set in here, which is just about 5,800 Kelvin. The curve is drawn for us. And the peak wavelength is a half a micron, which is 500 nanometers. And they've shown the visible spectrum right there. So it's right smack dab in the middle of our visible spectrum. And that's kind of a chicken and the egg sort of thing. what we believe, we've come to believe due to Darwin and other people, is the reason we have an eye who is sensitive to these frequencies is because of the temperature of the sun and the peak wavelength that it gives out. We think that over time on our retina, the cones and the rods have adapted themselves through evolution in order to be sensitive to the wavelengths emitted primarily by our sun, the peak wavelengths that are put out. Now, just to be clear, the sun is putting out infrared radiation, right? And you feel that is heat. And it's also putting out ultraviolet radiation. That's why I guess you use suntans, sunscreens and things like that with high SPF to protect yourself against the damage to your skin from the ultraviolet as well. But the majority of the radiation coming from our sun based on its temperature is in the visible spectrum. Okay, the part of the electromagnetic radiation spectrum that is which our eyes have adapted to over the millennia in order to be sensitive to. Okay, why I like this simulation over some others I've seen is so let's uh, let's take it down a notch to a lower temperature like that of perhaps a light bulb, and you can see two effects occur. The first one is look where the peak wavelength is now. It's now out in the infrared. Now, there's still plenty of energy in the visible from a light bulb, but if I take the temperature of a light bulb, which is about 3100 Kelvin, the curve gets much lower in intensity. And just to prove it's still got the same shape, I can scale it up, and it's exactly the same shape. It's just been shifted to higher wavelengths. Just kind of an interesting artifact. Still plenty of visible, but the peak is actually in the infrared. That's why you can, of course, burn yourself from a light bulb when you touch it. On the other hand, if you go to a different star, maybe one like Sirius A, and you can see the curve. I better zoom out a little bit on this curve. You can see that the curve still has the same shape. Planck's curve fitting to these shapes still holds, but now the intensity is much greater at the peak, okay? And the wavelength has moved into the ultraviolet region. It's about 290 micron. And so obviously we don't see most of that. We can still see some of the visible light from a star because there is still some of the radiation from the star is in our optical band that we call visible light, but the peak is in the ultraviolet. Now, if you ever saw the movie Predator with Arnold Schwarzenegger, the presumption there is that that person that he was fighting in the movie came from a planet that was on a star system that had a temperature closer to that of a light bulb. And so let's get it right in there. And so that predator that Schwarzenegger is fighting actually has a sun in that solar system that's a little cooler than ours. And so the peak of the wavelength that's emitted by that of the wavelengths emitted by that star were in the infrared, and so that meant that that being's optical sensor, its eyes, had adapted with a visible spectrum based on their sun that was a little higher in wavelength, okay, into the infrared region. And so then when this predator looks at Arnold Schwarzenegger, he's actually seeing the infrared signature from a human being at 37 degrees Celsius, the normal body temperature. And that's what's glowing for that being's optical sensor. It's an interesting piece of science fiction based on this law and science fact. Okay. And so we understand that our optical sensor has over time developed to match exactly that of the primary wavelengths emitted by our sun. Okay, one other thing. One of my dogs decided to come visit us here this morning. How you doing? One other thing that we can do with this little simulation is I can use the Stefan Boltzmann law to find the area under the curve, and it's printed out over here. So if this is power spectral density and you find the area completely under the curve, you can see you get an intensity in watts per meter squared. And for this particular case, you get 6.87 times 10 to the seventh watts per meter squared is the intensity being put out in all directions from the sun. And so if you wanted to figure out how much is coming to Earth, remember all directions means that the area is the area of a sphere around the sun. My area of a sphere is 4 pi r squared. And then if you want to figure out how much we're getting it on the Earth, you got to look at the cross section of the Earth's disk, essentially, and that would be the fraction that we're getting. The reason I'm going through that is because at least one group here in a second is going to have a problem where they're going to have to figure out, okay, out of the intensity from the sun, which you should get a number about 10 to the 7th watts per meter squared, what fraction of that is falling on the Earth? And you'll see that in a second. Any questions about everything, any that I've said? The three rules we've got, the three laws here, are the Wien displacement law, which allows us to calculate what the peak wavelength is if we know the temperature of the thing, that is the black body that's emitting that wavelength. The Stefan-Boltzmann, which allows us to get the total intensity being emitted across all wavelengths. And then Planck, who gives us what the shape of the curve is. He tells us what the intensity is in a 1 micron or 1 nanometer band, depending on what the units are on the y-axis here. Okay, and that's why it's called a relative intensity, sometimes a spectral intensity, a spectral power density, a power spectral density. I've heard all those words for that script I. If we got those three things, we've got what we need on black body radiation. All right, so here's the problems you're going to do, and I'm going to break you up into three groups here in a second. But first, I want to share my screen so you can see what you got. Share. And screen mirror here. There you go. And okay, there are 3 pages to this handout, and I can stop that, get rid of that. I'll even turn it sideways for me so it's a little bigger. And so each of the 3 groups is going to do 1 page, which is 2 problems, and you can see each group has one where your first problem is to figure out either the temperature or the peak wavelength based on some information you're given. And then the second is to figure the total power, the total intensity first, and then multiply by some area in order to get the total power being emitted, and then compare it to some things. And so the second group is going to look at a different object. First group is going to look at a white dwarf star and the human body. The second group is going to look at our sun and look at the intensity emitted by the sun, get the power output from the sun, and then time permitting, do some more calculations. And the third is going to look at the Earth. Our average temperature, we always talk about room temperature is 20, but apparently if you average the Earth's temperature, it's 15 degrees Celsius. Well, that has a peak wavelength that we emit at as well. We don't see the Earth as glowing though, because that peak wavelength is outside the visible spectrum. If we had an optical sensor that was sensitive to that wavelength, we would see the Earth as glowing, okay, but we don't. So we'll figure out what the peak wavelength is for the Earth as it radiates, and then figure out what kind of power and intensity the Earth puts out. And what I want you to do is a global warming sort of question, this third group, interesting problem. Okay, if you can figure out, and by the way, group 2, whoever's in group 2, here's your answer for what kind of power the Earth should be receiving from the sun. Okay, and then you want to figure out, okay, from part A there, how much are we radiating away using the Stefan-Boltzmann law? Okay, should we be cooling up or should be heating or cooling down? Which should we be doing? And it's an interesting calculation for the kind of the first estimate of should the Earth be heating up or cooling down? Should we be seeing global warming or global cooling? And then talk about any differences. I also threw, so you don't have to run for equations, the constant you need for Wien's displacement and the total the Stefan-Boltzmann constant for total intensity. So you don't have to go running for constants. You just need a calculator to do the work. All right, so I'm going to finish sharing that. Everybody understand what we're doing here? So let's break out into 3 groups, since I got three pages. Each group does 1 page. Group 1 doing page 1. Anaya, Sam, and Shneha, you're in group 1. In group 2, we have Amaya, Justin, and Prince. And Max, you always seem to be in the group with just 2. So it's Max and Sayed, you're in group 3 doing page 3. Any questions on that? All right, well, off you go and into your rooms. There you go. Everybody's off.
I think the first
For the first one, what equation is it for the surface, whatever?
it is Wien's displacement law, the one that lambda with the maximum intensity multiplied by temperature will be a constant.
Gotcha.
We're looking for T.
Yep. All right, you guys are rolling. I'll leave you alone. Exactly right. In your case, you're given wavelength and trying to solve for T. Other groups are given T trying to solve for wavelength. It's not the most difficult calculation, is it? Just watch your units. I'll leave you guys. Good work.
All right.
Yeah, we use Wayne's law. Am I pronouncing that correct?
Yeah, the one for the constant.
We have T, and then we find lambda. I think that's what we do.
Yeah. I got 499.7 times 10 to the minus 9. Just check me on that.
And then K is that a unit or
Yeah, that's a unit.
off?
Times a Kelvin, though, right?
Yeah.
Yep. And now you divide it by your temperature. Yep. All right, you got it. I'm going to leave and go on to the next group.
What was the answer for that?
So someone in the infrared, right?
Yeah, but I don't know why this is not giving me all of the units.
I'll just tell you that is a good number. Most people in the infrared use microns, micrometers. So it's about 10 micrometers, right?
Yeah, it's about there, yeah.
And so that's, I think you're definitely in the infrared.
Great. So yeah, we were just looking for, this falls under, I just didn't know where this actually would fall on the spectrum. So I was just looking at this, but it is, as you said, it's definitely infrared. Okay, great.
Yeah. All right.
Awesome.
So you go on now, you're going to do the Stefan-Boltzmann law, and I'm going to let you play with that for a little bit. I'm going to go back to one of the other groups.
Yeah, that sounds good.
Thank you.
All right, let's move.
Did was P equals, so right, P equals, and then that, you know, that thing, that that constant that looks like a O. Yeah, I'm pointing to you.
Sigma.
The 5.67, that constant.
Sigma.
Yeah. Sigma, yes. And you multiply that by T to the 4th power, and then times 2 pi r times H plus R.
You've taken T in Kelvin, right?
T is in kelvins for me, yeah.
Cool.
Okay, and then we have the cylinder. Okay.
Yeah.
Times it was 2.
2 pi r times, and then in parentheses, h plus r.
Okay.
And I just plugged in everything. And for the temperature, use 310. I guess it would be more precise if you did 310.15. But I just used 310 in my calculation.
Three 10.15.
Yeah, Kelvin.
Yeah.
Tucholsky,
Yes.
can I check my answer for 2 before we like continue with it?
Sure.
I got 804 watts.
Looks good to me.
Okay.
So I got as well. I got 804.2, but it depends.
Yeah, I didn't use 310.15 for Kelvin. I just used 310 Kelvin.
Yeah, in fact, I just used 37 and 273. So that's close.
And
enough.
then for the next one, did you, for your 2 energies, was the bigger one the first one?
Well, which is the first one?
The energy from the person one day?
In one day, I had,
6.95 times 10 to the 7?
Yes. And
then for the second one, it was smaller. It was 8.34 times 10 to the 6?
Yeah, exactly. And so that means if you had an emissivity of 1, just because you were radiating energy, you would burn more than 2,000 kilocalories of energy. Okay. The problem is, of course, you're not a black body. You don't radiate perfectly, but it does give you a scale of about how many calories that corresponds to. So yeah, finish it up. You guys got them. I'll leave you alone here.
Well, maybe you can annotate if you want.
Agree with that. Just about 500 nanometers. Yep. Okay. Yep. Okay. Exactly right. I'll leave you guys alone. I agree with that area. That looks good. And I agree with your wavelength from number 4. So far, everything you got is perfect.
Okay.
Something in the area of 5.09, 10 to the power of 14.
Yep, that's what I got.
Perfect. And then move this around a little bit, and
Yeah, I should have given you more room there. That's my bad.
that's fine.
Yeah, I remember Sam mentioned I need to give you guys more room to work sometimes.
Yeah. So yeah, what we did essentially is we found the intensity of the the output of the Earth, and right now we're calculating the area of a sphere, and then we're multiplying it by our intensity to get the kind of like the total output.
Total output
sort
power.
of thing.
Yeah. Now I agree with all your numbers so far. Yeah.
Awesome.
Yep. All right. The hard one will be that third one. We've got a few minutes, so think about that third one. You guys have the hardest one, I think. We'll see.
Great. No, I'm so lucky
Actually,
No.
you don't, because I gave you the number. It's group 2 that calculated that 1.8 times 10 to the 7th watts. You'll be able to compare. Should we be cooling down or heating up based on this? All right.
Great.
I'll leave you guys
Awesome.
alone.
Thank you.
You bet.
Thank you.
Fine.
Just, yeah.
Wow.
So that a -8. Yep. Okay. Yep.
Last thing you forgot to use the phone.
Okay.
Is my screen delayed? I'm confused.
I think it's delayed.
Yeah, it looks like it's frozen. Hold up. I'll have to reshare it. Share that again.
Yo, Amel, tell me how you going to do numbers, the 6th one. Last question.
Done with the 5th one?
No, the
Well,
other
we're
one.
basically done. I have all the numbers. I just need to multiply them together.
Okay. Yeah, and what your math is right. The only thing is what area are you going to use to get the power, because you're calculating the intensity, watts per meter squared, and so you need to multiply by the surface area of the sun.
Isn't it the surface area of the sun? 4 pi r squared?
4 pi r squared, and yeah, you use the 6.96 times 10 to the 8th meters for the radius, and that should give you the power being radiated. If you're frozen up, we won't wait for that. We'll move on.
Okay, there you go.
All right, there it is. Mirroring.
Is it delayed again? I'm confused. Can you guys see the screen?
It's blurry because you need to hit the screen mirroring.
I already did.
Then make it go away then. Just kind of swipe it off to the corner. Or just tap on it.
It's just very delayed. It's so weird because like I did all that.
Okay, all right. Now it's screen mirrored, and you just got the tablet. Then swipe that away, and you should be good to go. Just tap on your screen.
I think it is very delayed because I'm
okay.
on.
So you're seeing it. It's clear to you right now.
Yeah, it's fine to me.
Okay. Yeah, it's just your airdrop is slow then, or whatever that's called. AirPlay is what Apple has. What number did you get though for the intensity, and then what number did you get for the power?
64,170,190.57 for the intensity.
Okay, so you got a 6.4, and then
there you
there
go.
it is. All right. So let me count 1, 2, 3, 6, 7. Yep, that's a good number for intensity. And then now you got to multiply that by your area to get your power.
Maybe my internet that might be slow. I don't know. Yeah. Or Zoom.
You can just say what the words are. You just you multiply that area by that intensity, you get a power. So you don't necessarily have to write it out. but have the number ready.
Okay.
All right. All right. I think we're going to meet back up here. So I'm going to end the breakout rooms. 1 minute. And I'm going to leave.
Yeah.
So what do you think? Are we warming up or cooling down?
Yeah, we decided it's cooling down.
Yeah, it should be, right?
It
It's,
should
that's
be. I mean,
based on
yeah, I mean
radiation.
it's
Yeah.
yeah. It I look at it as a way of like the output is more than the input. So
Okay.
it's obviously
Yeah,
cooling
exactly.
down.
Exactly. Definitely cooling down. And so then the question is, why not? And we'll talk about that. Why aren't we cooling
Mhm.
down?
Oh, so this information is how up to date is this? Because I was curious to know.
No, I think that's the Earth's average temperature changes. Obviously, that's the whole global warming thing. But based on a
Yeah.
15-degree average temperature, you can see we should be cooling down. But this is the point of global warming. Why aren't we? And the answer is atmosphere, right? Well, everybody's coming
Mhm.
back. Right. We have a greenhouse basically with our atmosphere. So we radiate away, but then it reflects off our atmosphere and comes right back down to the surface of the Earth. And this is one of the things that I didn't realize. Who's not here yet? We're 1, 2, 3, 4, 5, 6. Everybody's here. Okay. One of the things I didn't realize, and it was Neil deGrasse Tyson in when he redid the Cosmos series. If you haven't watched it, I recommend. It's good. It's free. I think you can go to National Geographic Channel. But in any event, the point was, why is Venus uninhabitable? Why is Venus so hot? And I just always assumed it was because it was so close to the sun like Mercury. And that's not the reason that Venus is so hot. If Venus didn't
Because of
have
the
its
atmosphere, right?
atmosphere, it would be very similar in temperature to the Earth, maybe a little bit warmer, but it wouldn't be so uninhabitable like it is. But it has all that CO2 in its atmosphere, creating a greenhouse, so it doesn't radiate. It just gets hot. And that's the primary argument for me on truly global warming, because you've just shown, and we'll see their numbers in a second for everybody else, that based on the Earth's temperature, we should be radiating more power than we're getting from the sun. Okay. And so we should be cooling down. It is the atmosphere that reflects our radiation back to us, which causes us to stay stable and, in fact, is heating up right now. And the more CO2 we put into the atmosphere, the greater that reflection from the greenhouse effect is, and the warmer we're going to be. And if we're contributing to that CO2 because of humans on Earth and cars and planes and everything else, well, then we are contributing to the rise of the global temperature. But that's for another topic. But that is kind of the bottom line for some of the numbers you did here. Let's go around first of all and just compare. Let's do your first calculation, either what your temperature was or what your wavelength is. So group one, you had the 15 nanometer. It's a white dwarf star. That's the peak wavelength that we got. What temperature did that have?
I'm getting, after I rearranged,
Yeah.
1.932 times 10 to the temperature.
Yeah, temperature. Yeah, you're at 1.93 times 10 to the what? Fifth, right? So
I wrote meters on it instead of Kelvin. That's what confused me.
That's all right. But the bottom line is our sun is something like 5,800, 5.8 times 10 to the third, and a white dwarf is 1.9 times 10 to the fifth. So it's not quite 100, but certainly more than 10 times the temperature of our sun is how warm a hot white dwarf is. And that's the kind of calculations that astronomers do. And so if you like this, take Dr. Kem's astronomy course someday. All right, so second group, let's see, second group, you guys had our sun, and you were calculating what the wavelength was, which you kind of knew from what I'd showed you. But what'd you get for your number?
We got 499.7 nanometers.
just about exactly 500 if you round it off, but 500 nanometers, right smack dab in the middle of the visible range, right? Okay, and so that we kind of knew that one, but you proved it. And then the last one, the last group, you were at 15 degrees Celsius, which is the average temperature of the Earth, to 2 digits anyway. And what wavelength did you get? I guess that's max, or were you working?
We got 10,057.26 nanometers.
Yeah. So
yeah, I would. Do you want to show the working, or are we
no,
just saying answers?
I saw that. Just what your number is for everybody else. It's about 10. That's about 10 microns, right? Which is well into the infrared. And so that tells us definitely the Earth radiates in the infrared. If we had an infrared camera sitting on the moon, the Earth would be glowing, right? As it looked, looking back at the Earth. Okay, and that's what that tells us. Okay, so those are the good numbers for the first one. All right, now if you want, I guess, Sam, if you want to share your screen for problem 2.
Sure. Oh, I'm not allowed to.
Each problem 2 here. So
I
need to give you permission, don't I? Sorry.
Yeah.
Share screen. Go ahead. All right. Yep. And so, want to talk to it real quick?
So the first one, you guys understood that equation. For the second one, to find the power radiated, you have to change, first of all, the temperature to Kelvin, and then use like that Boltzmann equation, which is basically like the radiation times the area. And for the area, you just assume that the human is like a cylinder with a given radius and a given height. And when you plug everything in, you get 805.73 watts.
Okay, that looks good. And their third part was to compare that to like how much energy you might take in from 2,000 kilocalories of eating. You eat some food that brings in, and so they're just kind of comparing those two numbers, and you see, they did the conversion to days, because what's 86400? That's seconds in a day, I guess.
Seconds. Yep.
Yeah, seconds per day.
Yeah.
And so they see that in a day, that means that you're radiating away almost 7 times 10 to the 7 joules, right? But if you take in 2,000 kilocalories, which is a pretty good meal, what are you radiating away? Like a tenth of that, right? So just on radiation, we should all be losing weight, I guess, right? If we just sat around, and that means no exercise. That's just black body radiation. Why don't we lose that much energy? Why don't we lose weight?
We're not black bodies.
We're not black bodies. Yeah, and we're not. We don't have a perfect emissivity of 1. We have something way less than that. Okay. Any questions on their problem? And you're all going to be doing basically the same calculation. So let's move on to group 2 then. Who's group 2? Who's got the lead on that? That's just Jastins. That's right. He was having some screen. His AirPlay for his tablet was taking a long time, but hopefully it'll pop up here. And what time is it? Yeah, why don't we just talk through your numbers? What did you get for your ultimate power?
I think for power we got 3.91 times 10 to the 26 watts.
Yeah, exactly. Doing exactly the same calculation, figuring out what intensity was. There it is. Epsilon times sigma times t to the 4th. They got that much intensity, and then they multiplied by the surface area of the sun to get the 3.9 times 10 to the 26 watts. All right, now just real quick on their last one, they had the hard piece here, but I do want to annotate. So where's my annotate button? Maybe I'm not allowed to. Yeah, I can annotate. So what we're saying here is, let me get a pen. if there's the sun and it radiates out to where the Earth is, so there's the Earth and there's the sun, that would mean I would take that power and I would divide that power, divided by 4 pi times the distance out to the Earth. So that's sun, Earth here. I hate that it puts my name right when I'm annotating, okay? And then I guess if I multiply that, that gets me an intensity out at the Earth's radius, right? You basically undid this calculation. That was right at the surface of the sun. And now I'm going to redo it so I get intensity out where the Earth is. And then if I multiply by pi times the radius of the Earth, which is our area, which is, you know, what little disk we present in that sphere, okay, what we'll get is about 1.8 times 10 to the 17th watts at the Earth every, well, that went away. Oh, there it is. Okay, it's back. All right, so that's where the number for the third problem goes. And I think that's Max and Saeed. So if you guys want to start sharing yours.
Yeah, just a second.
Yeah, it's coming. And I'm keeping you a couple minutes over. We're already 4 minutes over. I apologize for that. But we'll just get these answers out and we'll we'll see their conclusion, which is what we were talking about when we were reconvening. All right, there it is.
All right, so for the seventh one, that's the same thing you guys have been doing already. So it's the constant divided by the temperature in Kelvin.
Yep.
And we came up to a lambda max of 10,057.26 nanometers. Max, you want to go ahead and explain this one?
Sure. So we used the Stefan-Boltzmann law, and T was still 288, and epsilon and sigma were just constants. So we got the intensity, and then we multiplied that by the surface area of the Earth and got 1.99 times 10 to the 17th watts for the power output.
Yeah, so we're just radiating that much power, energy every second, okay? And then the conclusion, though, should we be heating up or cooling down? Based on the calculation I just did, we're getting from the sun 1.8 times 10 to the 17th. And Max just said we're radiating at almost 2 times 10 to the 17th. So we should be, our output, we should be cooling down. And that's the whole discussion about global warming. We would be if it wasn't for the greenhouse gases in our atmosphere, which reflect our radiation right back down to the surface, okay? Should be, but we're not. And the problem is, are we making that greenhouse worse? And are we increasing the temperature of our planet to a no return point like Venus? And are we eventually going to make ourselves uninhabitable like Venus? All right, of course, Venus gets its carbon dioxide from naturally occurring sources, but ours, we think a lot of them are because of man's presence on the surface of the planet. Hey, that's all I got today. Sorry about keeping you 5 minutes over here. We'll see you on Wednesday. No new, there is a couple videos to watch on YouTube. You don't have to turn in this worksheet. I'll just put grades in Canvas just from what you presented here. And we'll see you on Wednesday, ready to do some calculus, ready to do some integrals, ready to take some derivatives. All right. Have a good day. We'll see you then.
All right. Thank you.
You bet.
A question I had. Nice feedback for a question I had.
Sure. Go ahead.
Okay. Regarding the question where the Earth should ideally be cooling down instead of heating up,
right.
But how is it possible that the Earth was emitting more heat than it received? Like calculation-wise, it made sense, but
yeah. So where's it coming from? Is that, well, remember, part of the Earth's heating also comes from its taking power from the sun over time, right? So it heats up from the sun, but it tries to radiate out, but then that heat gets reflected right back down to the Earth. So it's almost like we're getting a multiplication of the heat from the sun based on our greenhouse, our gases in our atmosphere. So that's one effect. The other effect is, remember, the Earth's core is very warm from its formation. Okay, if you little, I'm not an astronomer, so I'm a little bit out of my depth here. But when the Earth formed after the Big Bang, as the solar system cooled down from the massive energy that came from the Big Bang, some of that energy from that is still stored at the center of the Earth. The center of the Earth, we believe, is molten because it's so warm. And so some of the Earth gets heated from geothermal from the ground. Okay, that's an effect as well. I still think the bigger effect is that the sun radiates on us. We would re-radiate it out, except for the fact that we have an atmosphere that traps it and reflects it back to us. Okay, I think I answered your question, I hope, because you're like, well, how did we get a higher temperature to 15 degrees, which allows us to radiate more than we're taking in the first place? And, you know, on day one, that probably wasn't true, right? And I'm not sure where in the development of the Earth came upon an atmosphere that was what it is today. But obviously there was a period of time where we were just cooling down as an Earth. And then at some point an atmosphere came to be. And at that point, once the atmosphere came out, that's when we started heating up, okay, and came to where we are right now. But we're still, if you look at those two numbers, they're fairly close to each other, right? One was basically 2 times 10 to the 17th. The other was, and that's our radiation number, and our other number was 1.8 times 10 to the 17th. So those two are kind of close to each other. That's what astronomers call the Goldilocks zone, right? Where we're just getting enough, right? If we were much further out, there'd be no chance we could ever heat up to be habitable. And if we were any closer into the sun, it would be so hot that it'd also be uninhabitable. The fact that those two numbers are reasonably close to each other is why the Earth is a habitable planet. And so as we're looking at other solar systems to see where habitable planets might be, we're looking in a range where the radiation and the absorption of energy from the star that's at the center is close to each other. And then there's a possibility that, you know, the planet could be inhabitable by beings like us that need, oh, I don't know, 70 degrees to be comfortable, rough, right? And that's kind of what when we're looking for other solar systems to look for life, that's what we're looking for. That's the so-called Goldilocks zone. Does that make sense?
I had another question.
Okay, go ahead.
How I hope it's not taking too long.
Oh, no, it's fine. This is normally where office hours are, so this is fine. Go ahead.
So when Planck came up with his equation for intensity of radiation,
Okay.
he assumed oscillators inside the black body.
That's what he's thinking. Everywhere on the inside of the cavity, right? Let me share a screen here. And to be honest, some of this is a physics class for another day. Okay, when you get to take your thermal physics class, you'll actually prove this more rigorously. But this is what Planck looked at. He looked at a cavity like this one, right? A black body cavity. And he said, all along here on the inside, the atoms are shaking back and forth, oscillating back and forth, every one of them. Okay. And so he looked at, well, what's the energy of each oscillator? And determined it had to be this constant times whatever the frequency of the oscillation was. Okay. Yeah, so all around here, it's all 3 dimensions of this cavity, little oscillators at the surface, which are vibrating, and that's where the total energy is coming from. That ultimately is the radiation, the thermal radiation. Okay, was that what your question was?
My question was that, like, obviously there's no like actual oscillator inside the black body. So where does that analogy Planck came up with, where does that translate physically? Because when I look at the equation in the denominator, it actually reminds me a lot of a damped oscillator, the equation we have for a damped oscillator.
Okay,
But
a little bit, yeah.
nothing physically oscillating in the sense that Planck thought of, right?
Well, I think, well, remember, what is temperature a measure of? If you had a container of gas, right? Those are all, and I'm just going to draw a few gas molecules. The temperature is exactly defined by how much kinetic energy those molecules have. They're constrained in a temperature, so sometimes they're moving along in straight lines and sometimes they're oscillating back and forth. Okay, so temperature had long been known to be proportional to kinetic energy, and the kinetic energy could be translational, it could be rotational, and it could be oscillatory. So, yeah, oscillatory. Well, at the inside of a black body, the atoms aren't jumping off and moving in a straight line like gases can. Really, the only thing they can do is oscillate. And that's why his assumption was they were oscillators. A gas or a liquid, you can have rotations and translations, but the only thing you can have on a solid is a vibration. And that's a part of solid state physics that is, I mean, it's a truth, right? Unlike fluids, liquids and gases, all you can have is oscillation, okay? I'm not sure if I've answered your question yet, but that's why he focused right in on simple harmonic motion, because it was a solid. These black bodies are solids. They're pieces of metal or pieces of some kind of composite or maybe even plastic or some real thing that's solid. And so the only thing they can do at the surface is vibrate back and forth. Very small vibrations, but the greater the vibration, the greater the temperature. Okay. And in terms of that function, the function that's 1 over e to the, it's really an energy of an oscillator divided by the thermal energy. And I always have to look, is it +1 or -1? Because, yeah, -1. Yeah. Yeah, it kind of has to be -1, I guess. So -1. I think this is just curve fitting. He had some empirical data and he literally was just looking for a mathematical curve fit. And so that's the one he chose. Okay. I'd like to tell you there was something, even if you listened, if you read what Planck said about his work, he described his work as insightful curve fitting or insightful making the data fit the math. And the insightful part was that energy of the oscillator right there divided by the thermal energy. And so that he went looking for a math function that had that relationship is kind of the key. Does that make sense? I mean, he really was just making that fit the shape of the curve that was in the data that he knew at the time, right? Making that shape of wavelength I, and he knew that had to match. And so that is the math function that will give you a curve that's shaped like that. Does that help? Yeah, yeah. A lot of it is I can't do much more in terms of a rigorous proof because that's a course you're going to take in the future called thermal physics, and I almost guarantee you that whoever teaches that course, probably Dr. Tech, he will go through this in a much more rigorous derivation. And so it's a great question. It's just you kind of have to wait for the answer until you move along in your physics. Okay. All right. Any else?
Black body.
What's that?
What if we have a liquid black body?
You know, that's an interesting question. Then you might have something other than oscillations, and you might need another term up there. Is that, yeah. So you might have, you know, maybe the liquid molecules can rotate right around. Again, you'll study this in the thermal physics class. The guy who came up with this idea is Boltzmann, and it turns out that the energy there is the number of degrees of freedom divided by 2 times kT. And that's just rough. Remember we said kT is thermal energy? Well, N here is, okay, do you have just oscillation? Do you have oscillation and translation? Because translation is really 3 degrees of freedom, right? You can go X, Y, and Z. Rotation, you can have, I guess, 2 degrees of freedom. It can rotate clockwise, it can rotate counterclockwise. And so, yeah, you would have to make a correction to that term right there if you had a liquid black body. Or, you know, and then it's like plasmas, things like that. if you try to treat a plasma as a black body because it's glowing, it would be more like a liquid. That would be an example of that. And I think you would have to correct Planck's equation to account for the fact that you have other what we call degrees of freedom. So I don't disagree with what your point is right there. That's this is for solid black bodies, which is our model, and we often do that in physics, right? We have to try to model something, so we come up with the most simple case, and then we look at other things like a liquid black body, and we modify it slightly. And so you'd have to correct that term a little bit, no doubt. Good question. All right, other stuff.
No, that's all.
All right, yeah, I wish you could take that thermal physics class right now, because a lot of your questions would be answered. I'm trying to think where it comes up. Dr. Tech taught it. I want to say he taught it either last spring or the spring before that, so it'll be coming up in the rotation again. And obviously, you want to take it because you'll get all the answers you need to this question. All right. What else can I do for you?
Thank you.
All right. You have a good day. You have a good day now.